Hi, welcome to Video 1 for Lesson 3.1. We're going to look at random variables of the continuous type. Continuous random variables can take on an infinite number of possible values corresponding to every single value in an interval. These are generally things that we measure. This is in contrast to discrete random variables, remember, that could take on only specific values that we could list and were often things that we count. One example would be my new puppy Scout's weight on July 1st. That is a random variable. It's continuous because her weight could take on any value between, say, 10 and 30 pounds. Another example would be the time that it takes to complete this Sudoku puzzle. Depending on the person, it could take any time from 0 minutes up to an infinite amount of time for someone who just can't ever finish that puzzle. Although many of the ideas that we're going to have are going to be very similar to what we did with discrete random variables, we are going to need different methods to model continuous random variables. We modeled the probability distribution of a continuous random variable, capital X, with a curve, little f of x, which is called the probability density function, or PDF for short. And here are the probability density functions for a number of different continuous random variables. Notice they're all smooth curves. For continuous random variables, little f of x is not the probability that the random variable takes on the value x. It was in the discrete case, but in the continuous case it is not. F of x is just the height of the curve at the point x. It's not the probability of anything at all. And probabilities are going to be found by looking at areas under the curve. So, for instance, if we want to find the probability that our random variable x takes on a value between a and b, then we are going to find that by finding the area under the curve between a and b. Since there's no area under a curve at an individual point a, the probability that x takes on the value exactly equal to a is actually 0 for all values of a. There are just so many possible values, an infinite number of possible values, that the chance that it takes on any particular one is 0. So we can only talk about the probability of x falling within some interval. We can't talk about the probability of x taking on a particular value. And when we want to find areas, probabilities with areas under the curve, the way we're going to do that is by using integration to find the area under the curve. So we want to find the probability that x is between a and b. We're going to integrate the probability density function f of x dx from a to b. There are times when we won't need to actually do this integration because we'll be able to work with tabulated distributions that are sort of special distributions, like the normal distribution and the t-distribution, those kinds of things. But if we are given just some sort of general probability distribution function, we can use integration to find probabilities. A couple of properties of probability density functions. One is that the function must be greater than or equal to 0 for all values of x. Also, the total area under the entire curve, it's going to correspond to the probability of our sample space, really, is always going to be equal to 1. But notice that there is no condition that says that little f of x has to be less than or equal to 1. It doesn't. F of x can actually be greater than 1 for some values of x because it's not a probability. Just as with the discrete case, in continuous random variables, we have the idea of a cumulative distribution function, CDF. We still use the notation capital F of x, and it's the probability that x takes on a value less than or equal to a specific number, little x. The way we're going to find it is actually by integrating from negative infinity up to the value x, the probability density function, little f of t dt. So let's look at an example with a continuous uniform distribution. Continuous uniform distribution has a probability density function that is constant on its support. If the support is an interval from a to b, then little f of x is going to equal 1 divided by b minus a for x that are between a and b. And this will give us, if we integrate this function from a to b, it'll give us a total area under the curve of 1. So so we know that it is in fact a probability density function. We use the notation x is distributed u for uniform on the interval a to b. Now suppose that we're going to use a random number generator that randomly generates a value between 0 and 5. Then our random variable x is going to be uniformly distributed on the interval from 0 to 5. This means that our little f of x equal to 1 over b minus a is going to be 1/5. And we can see that the total area under this curve is 5 times 1/5 is 1. And we can see that our PDF, little f of x, is constant over the entire support. Now if we want to find the probability that x takes on a value between 2 and 2.5, that's going to be the area under the curve between 2 and 2.5, and it's shaded here. Now, we can find that by integrating from 2 up to 2.5 our f of x dx. So plugging in 1/5 for f of x, this gives us 1/5 times 2.5 minus 1/5 times 2 gives us 0.1. And that's the probability that x takes on a value between 2 and 2.5. If we want to look at the cumulative distribution function, the probability that x is less than or equal to a specific value little x, we integrate from minus infinity up to x, f of t dt. So this is going to be 0 for any value of x less than 0, because we can see there's no area under the curve at that point. And it's going to be equal to x over 5 when we have x that's between 0 and 5. And it's going to be equal to 1 once x is greater than or equal to 5. So there's our cumulative distribution function. If we want to find the probability that the random variable takes on a value less than or equal to 3.1, so that's capital F of 3.1. This is the area under the curve between 0 and 3.1, all of the area under the curve to the left of 3.1. We can see that's 3.1 over 5, which gives us 0.62. In our next video for this lesson, we'll take a look at mathematical expectation, specifically the mean and the variance for continuous random variables, and also look at moment generating functions for continuous random variables. Bye.